Hello, stats class. This is Mrs. Crum, and here's the notes for 3-1B. Funny story, I started recording these notes earlier, and I did not have my mic on, so I wrote out the whole thing, and then I went to watch the video, and nothing, no sound. So I'm going to do it again, but I'm not going to write it again. If you need me to go slower, just pause the video, obviously. So correlation is a way of measuring the strength and direction of a scatter plot numerically, because it's kind of what we've been doing is informal, just saying strong, moderate, weak, positive, negative, and this is more of a numerical measure. So the extremes are, you can have very weak, no association. This one's really fun to draw. You just put lots of dots, and if it starts to look like it's positive, then put some more dots here and here to make it more negative. Just random dots. You can't tell if it's positive or negative. That would be no association at all. And the correlation is called R, and that would be a correlation of 0. It means that X does not help us predict Y at all. And so that's like no relationship at all between the variables. Correlation of 1 looks like a perfect positive line, and you've seen that in algebra class before. You're not going to see it so much in this class. Perfectly positive is a correlation of 1. And perfectly negative, again, you'd see that mostly in an algebra class, is a correlation of -1. In statistics, we will very rarely see these two situations. We usually expect something in between. In fact, I should have made this a less than without the equals, because we're hardly ever going to see it equal to 1 or -1. So the calculations for this, actually, before I do the calculations, I'm going to show you a few more examples in the book. This is page 151 in your book. So here's a few examples just to get you a feel for what those correlations might be like. Here's another example of 0. This is a -0.3, very weak negative. You can barely tell it's negative. Here's a positive 0.5, weak positive. Think about it as a percent. 50% positive trend is what that's saying, is one way of looking at it, and that's not very good. Here is a -0.7, so a little bit stronger. You can definitely tell it's negative, but still not very strong. And I'd say that's moderate, and this one would probably also be called moderate. This is a 0.9, which surprises people sometimes. Sometimes you would expect 0.9 to be stronger than that, but it's not. And here's a -0.99. That's very, very strong, but still not perfect. So estimating is difficult, and I would generally tend to advise you to estimate less than what you think it really is, or closer to 0 than what you think it really is. So a lot of people might look at this and think it's a 0.7 or 0.8. It's really, you know what, I said that backwards. It's really 0.9. So estimate bigger than you think it ought to be, or closer to 1. But there's some examples just to get you the general feel of it. But we're going to talk next about how to calculate this. And I put some introduction to this in the warm-up, which I hope helped you. The calculations are based on z-scores. So we did something like this in the warm-up where you had to take your data from the forearms and forearm plus hands and find your zx, which is the z-score for your x value. And that's the same formula we've used before, x minus the mean of the x's divided by standard deviation of the x's. So like just looking at the x's, if you have a table of data with a column of x's and a column of y's, you're just looking at that first column only to find this zx. zy, same thing, z-score based on y. So you would do y minus, instead of x bar, now it's called y bar, which is the mean of all the y values. SY means the standard deviation of all the y values, and you could find those numbers by doing one variable stats on your calculator, or sometimes they'll be given to you. So ZX and ZY, for each individual point on the plot, you multiply them together. And that was the very end of the warm-up. I asked you to multiply them together, and then you add them all up and divide by n-1, which we've seen that before. It's 1 less than how many data values. So that is the official formula for finding R. You are not going to need to use the formula much beyond the first homework for lesson 3-1B. Has some in your homework where you have to do it by hand with very small data sets, just to kind of get the idea of why this formula makes sense. I'm going to do a very small data set example right here. So I will leave it up to you whether you want to write this part down, or if you want to just watch this part, that's fine, because the calculator can do this, right? But we're going to do it by hand once in the notes and maybe a few times in the homework just to get the general idea. So I've got my X's and my Y's. I chose a data set that has only 4 points. I graphed it over here so you can see what those 4 points are. What you do is you find the mean X, find the mean Y. In fact, I will remind you of how to do that on the calculator. So I have list 1 is X and list 2 is Y right now. And to find the mean X, you could do stat calc 1 variable stats, or actually you could do both at once with 2 variable stats, which is kind of a handy thing to know. 2 variable stats, list 1 and list 2, and it will find the mean X, which is 3.75, that's where I got that number from, SX, which is the standard deviation, and then if you scroll down, it will do the same thing with the Y's. So Y bar, which is the mean Y value, 5.75, and SY, which is 4.5. I got those numbers by doing 2 variable stats on my calculator. And then I found the z-scores. So what I did is I made the table in the calculator do all of this, but if you were doing it by hand, you would do each of these individually. And like this one, for instance, came from the X value minus the mean of X divided by the standard deviation of X. And here's another one that I showed work on just so that you could see where that came from. I did it this way with my calculator. I went over to the very top of list 3. In case you didn't know, you can do that. And you can tell it to do parentheses, list 1, that's second one to get to that, minus the mean, which was 3.75, and divided by the 2.75. That's just typing a formula to tell it how to fill in this column. So I did that to find the zx's, and then I did it again to find the zy's by doing L2 minus the mean of L2, which is 5.75, parentheses divided by the 4.5. So that's a shortcut that you could do either here or on a spreadsheet if you wanted to, and that just tells it how to fill in that column by using the formula. So there's the z's, x's, and y's. So before we go on, one of the things I had you do on the warm-up is I had you draw where the mean x line is. So x is 3.75, that's what this dotted line represents. Y is 5.75, that's what this dotted line represents. So this point right here is above the mean in both directions. It's positive, positive, and that is the last point on the table, positive, positive. When you multiply them together, you get a positive. This one also multiplies to make a positive because it's negative times negative. That's this point down here. It's below the mean in both directions, and so that's a negative, negative, but when you multiply them, you get a positive. And that's one of the things that is useful about showing you this example is that this point and this point are part of the positive trend. You can see that if you only had those 2 points, it would be perfectly positive. And then these 2 points are, it's kind of like they're voting for a negative trend. This one has a negative zx, that's the 2, 6, which is right here, negative zx and positive zy, really small positive zy. And when you multiply those, you get a negative result. And then this one is a positive zx and a negative zy. It's above the mean for this, and it's below the mean for y. And so because of that, when you multiply them, you get a negative. So it makes sense, I hope, well, it makes sense to me, I hope it makes sense to you, that these, I'm sorry, my computer's making noise, but that's okay. Life goes on. But these are giving you more positive trend input, and these are giving you negative trend input. Okay? If I knew how to make that stop that noise, I would. Maybe I will try a few things. Actually, I'm just going to ignore it, to tell you the truth. So anyway, when you add all this together, you end up with a positive sum. And the reason is that these have more weight because they're further out. And these have less weight, and that's what's giving it the positive trend overall. So 1.84 added up. That's what I got, and I divided it by n minus 1, which in this case is 4 minus 1, which is 3, and I got my correlation, which is 0.61. So that's an example of if you were doing it by hand before computers, that's how they used to do this process. And it's kind of a pain, which is why I'm not making you do it very much of the long process. But I do think it's valuable to understand what these 4 quadrants are telling you, that these are positive votes, kind of, and these are negative votes towards the correlation. Here's how you make the calculator do this. And I apologize again for my silly computer. I might play around with that. If I unplug one thing, it might help. So let's talk about the calculator. Again, my data is in list 1 and list 2. If I go to stat, I'm going to show you the wrong way first. This is the first step, is you have to turn on diagnostics. If you don't turn on diagnostics, it will not work. Actually, I'm not going to show you the wrong way. I'm just going to show you the right way. So if you go to mode, and then further down on this list, there is a stat diagnostics on or off. That's only on the newer calculators like the TI-84 Plus, but probably not the TI-83. You can turn it on there, and right now I have it off, but I want to turn it on. If you have an older calculator that doesn't have this many things on the mode screen, you can go second 0 and then jump to the D's. So the D button is right here under the math button, and then scroll down until you get to diagnostic on. You want to turn on diagnostics and leave them on for the rest of this class, or rest of this year, basically. Diagnostic on. Now that it's on, I have my data in list 1 and list 2, and then I could go stat and calc and choose number 8. And this actually is a little bit of lesson 3 too, because this is how you get the regression line. I like number 8 better than number 4 because our book does it this way. I'll tell you why in the next lesson. A plus bx, enter, and list 1 and list 2, and enter. And it gives me the line of fit, which is great. It also gives me R at the bottom, 0.61. And look, that's the same R that I got before. So that's how you make your calculator do it. When the book says do it by hand, please do it by hand just so that you get that experience with the formula. I think knowing that it's z-scores multiplied and added up is valuable, but then most people just do it with the calculator, and that's fine. All right, so like I said, if you need to pause this and catch up a little bit, that's fine. Here's the last little bit of notes. The last bit is facts about correlation. Correlation is a number that represents a scatter plot, right? And it tells you the direction, positive or negative, because positive slope would be positive correlation and negative slope would be negative correlation. It tells you the strength, strong, moderate, weak, and that's kind of just estimating based on the numbers, and I showed you some examples of that where 0.5 is really pretty weak. Strong needs to be pretty close to 1. It does not tell you the other two parts of DOFS. So DOFS is direction, outliers, form, and strength. Outliers and form, the number tells you nothing about those. So a common mistake is for people to say, oh, it has a strong correlation, therefore it must be linear. But it might not be, and we'll talk some more about that as the chapter goes on. It doesn't tell you if it's linear or curved. It doesn't tell you if there's any outliers or not. It does not replace looking at the graph. So that's really, really important that you know that this number can only tell you these two things and nothing else. It does not matter which variable is which. So this is something that if we were in class, I would ask you this, and maybe somebody would tell me, if I switch the zx and the zy around and multiply zy times zx, that doesn't matter. When you're multiplying, you could multiply either direction and it doesn't matter. So that does not make a difference. It also doesn't matter what units you use. Units don't matter because we switched everything to z-scores. So like if I measured in centimeters versus millimeters versus feet versus anything else, it doesn't matter what units I used. The z-scores will come out the same and the correlation will come out the same. Quantitative data only. This is really important. We did categorical back in chapter 1 when we did two-way tables and segmented bar graphs, and we looked at them to see if we could see a relationship between those variables. And if there was a relationship, we called it an association. Do not use the word correlation for categorical because you can't do these calculations when you're working with words instead of numbers. This only works for numerical data. So if it's quantitative, you can say there's an association or you can say there's a correlation. If it's categorical, it's always association. So be careful about that. Don't use this word for just anything. It has to be for quantitative, which is basically what chapter 3 is all about, 2 quantitative variables. And last but not least, we'll talk about this some more as the chapter goes on. R is one of the things that's sensitive to outliers. If I move a point around, it changes the correlation a lot. For instance, if I move this point down this way, that correlation is not nearly as strong as it is when it's way out here. So that further away point makes a big positive contribution to the correlation, and that's why it is sensitive to outliers. All right, so that is it for the notes on 3.1b.